Good afternoon. We have here Jing, Shu, and Manu Batra, and they will be talking to us about Kubernetes storage cheat sheet for VM administrators, and they are both from Google, and they made a transition from VMs to pods. So pretty cool stuff.
Perfect. Thank you, Jeremy, for the introduction. Again, appreciate everybody being here. Part of the talk was more about, I spent quite a few years, just 20, working on physical machines, VMs, and about a year and a half ago or so, I landed up in container land. And I was looking to say, okay, if somebody has to start today coming from that, how can we draw parallels on how, at an architecture level, how things work in a VM? How can I look at that in a container world? How can I look at an operational level, allocation of volume, setting up quotas? What does it mean if I'm used to those things on a VM world, can I translate them in a container land? So the talk's more about that. We'll definitely have time towards the end for questions, so definitely feel free. We'll start with a quick, still learning the clicker. So a quick set of introduction. I'm Manu Batra. I'm product manager for 8s Storage and Hybrid at Google. Jing, you want to tell more about yourself?
Yeah, sure. My name is Jing. I'm Google software engineer. I work for Kubernetes storage lifecycle team.
Perfect. So moving on to the agenda. What we really want to spend time on is a little bit talking about why do containers need storage? Containers are supposed to just come up and go away and come back up again when you need them. Then we're going to dive into a little bit more around what does it mean to look at container storage at an architecture level and draw parallels from a VM standpoint. Moving on, I'll be talking more about at an operational level, talking about day 2 and day 3, how do we draw parallels at an operational level? Then what we really want you to work out is a small cheat sheet. When you talk to container folks, and they start using terminology, you can always look it up and say, I know exactly what you mean. So that's the goal, that we can let you walk out with a quick, small cheat sheet, not 40-page, just a quick sheet. So let's get started. So container storage, why? I talked about aren't containers epithermal, just there's no supposed to be state. Now, when we talk about containers, they still need storage depending on what type of workloads are configured, what workloads and applications they're running on. At a minimum, you need storage to have Kubernetes control plane. So etcd has to have it. So you need to have some base images when you boot up. You need storage for that. So that's at a minimum, please. That's what you need from a storage standpoint. Moving on, if you're running stateless applications, you don't need persistent storage, but you may need storage for stateless applications to run scratch space. You may need to store some logs, temporary data, while the processing is happening in the containers. So that's the second area where, depending on the application, if they're stateless, that's one place you might need storage for containers. Moving on, as we get into more stateful applications, you want to run a MongoDB, Cassandra, or MySQL in containers, you may actually need storage which lives beyond the life of containers. So this is where we talk about stateful applications and persistent storage. So these are the 3 scenarios. Like number 1, you absolutely need it. Number 2 and 3 depends on what the workloads, what kind of applications you're running on. I don't know, just do a manual clicking. So talking about, before we start deep diving into it, I wanted to spend some time on how the progression of containers is happening and what are becoming the acceptable norms around workload deployments. So talking about some storage attached patterns. Traditionally, if I'm an admin and I want to deploy some workloads, Kubernetes administrators would deploy workloads in containers, but the data was either living in, if you're running in the cloud, like a managed database service from a particular cloud vendor. That was one pattern for deployment. Moving on, there was another pattern where, well, I want to run my own databases, but I'm not sure should I run them inside a container Because I'm not sure, I'll just run it inside a VM. So one potential option was you could run a database inside a VM, but your workload is running in containers. You get the agility, the scale across them, and that's someplace, one configuration to do around the patterns. But as the CSI is maturing, as the CSI has now enterprise features like Snapshot, it's going into beta soon, there is a huge push and a huge ask for administrators to say, I don't want to look at two separate frameworks, one for VM, one for containers. As an application, can I have a consistent application framework all based on containers? So more and more admins are adopting to move towards running databases inside containers itself. So that's where you need persistent disks and where the life of disk is actually beyond just the container itself. So a lot of our conversations between Jing and I will be focused more on the third pattern today. So we were looking at many ways on how we dice and slice the whole model, and what we ended up doing was kind of drawing it in a pattern to say, at day 0, when you're thinking about deploying an application, what are the fundamental approach differences at an architecture level? So day 0, you're thinking about architecture, you're thinking about the design of an application, you haven't deployed anything yet. Day 1, you start to deploy your application, you start building the application framework, infrastructure framework. We'll talk about what are the differences at that level. Then we get to day 2. I start bringing applications, I start consuming my infrastructure with applications and framework. What are the parallels we can draw over that side? And day 3, as I start consuming, how do I start controlling and managing things at scale? I'm used to certain patterns on VMs. Can I translate the same concept? And what does that translation even mean at managing at scale levels, setting quotas and things? That's about volume management parallels around day 3. So day 0 is more at a design. Day 3 is more about when you're actually scaling and managing things at scale and trying to make sure things stay in a sane way. So that's kind of how we're structuring the talk. Jing, do you want to cover day 0?
Sure. OK, so day 0, let's start with storage architecture comparison. So this is in a typical virtual machine cluster setup, right? This simplified architecture view. The bottom layer storage, right? There's a variety of storage available. And on top of physical storage layer, typically there is a virtualization layer. It provides a unified interface for your virtual machine to access your storage, right? No matter what kind of storage underneath, right? You can access as file or block devices. And across these layers, and the data paths make available for your workload to access the storage. And on the other hand, there is also need a control path, right? So you can manage your virtual machine and storage resources. So typically, a control plane provides you a set of the so-called imperative APIs to perform some tasks, like you create virtual machine, create disk, attach volume to some virtual machines. Now, moving to container world, right? So on top of virtual machine layer, you have operating system. And then you can run a number of containers inside a virtual machine. And you can run your workload inside of containers. And across these layers, again, the data paths make available for your workload to access storage. And in order to, of course, manage your containers and its related resources, you need another layer of control plane. We call it container orchestration. So container orchestration will manage the container lifecycle and also through operating system and control plane at virtual machine layer, right, to manage the underlying storage system.
Move to the next one.
Yeah. So Kubernetes, of course, is one of such container orchestration system, right? So Kubernetes, a main difference is Kubernetes use Kubernetes with so-called Declarative API. So just in a minute, we'll describe what's the fundamental difference between Kubernetes declarative API and imperative APIs. And also for Kubernetes to be able to manage the underlying storage resources, right? It needs to communicate with the control plane at virtual machine layer. So the storage community initiated a standard to be able these two layers to communicate each other. We call it container storage interface. So it is cross-environment standardized interface to expose the file or block devices. So with this standardized interface, right, for storage, right, vendor just need to implement their storage drivers and to expose those services based on the CSI spec, and it can easily plug in, right, any container orchestration system. Okay, we just mentioned imperative API and Kubernetes declarative API. What's the difference? Right? On left side, right, it is a typical list of commands you can use to perform some tasks in virtual machine environment. And for Kubernetes, every resource is basically described as API objects. Here we have some examples. And for storage, later we'll explain those in a little more detail, right? We have persistent volume claim and storage class. And for your workload, you have pod that represent a set of containers work together. And you have other type of resources as objects. So what's the difference between these two? Let's use a simple task as example, right? You want to create a disk, and you want to make it available for your workload to access it. And in the typical virtual machine environment, right, you need to figure out what's the sequence of commands you need to run. Like here, you need to create disk, you need to partition, format disk, and attach disk to the node that where your container is scheduled to. What if there's some, when you run these commands, there are some failures, some problems, then you have to run your API again. Now in declarative API world, right, so it's changed the way of managing system. You no longer need to worry about or figure out the sequence of commands you need to run. You just describe what you want to achieve, what the state of your system you want to get. So for example, if you need a volume available, right, you just define a volume spec, right? Describe what kind of volume you need, what's the size of the volume, what file system you want. And the system, the controller, will figure out what to do and make it available. And if your pod need to use that volume, then you define your pod spec, which have a reference of your volume object. Again, the controller will just figure out what to do, and basically what you defined in your API objects, right, describe what's the desired state of your system. And the controller will compare the desired state and with the actual state and determine what's the action it need to take. For example, it need to attach a volume to a node and then format it with the file system you just requested, and then mount it. And everything is done by controller automatically. If anything goes wrong, the controller will just keep reconciling the states until it reaches the desired state. Yes. Yeah, this is just a control loop, right? It keeps reconciling. And now we already have idea of Kubernetes way of managing. And we move on to how we represent the volume in Kubernetes. And again, in virtual machine environment, right, you have two types of people, two different roles. Users, right? User care about like what kind of storage I need, whether it is persistent, or whether it needs to be a file or block, whether it needs multi or single reader writer, what's the size of your storage. And the user just kind of send this request. And the system in will need to figure out how to set up the storage, whether it is fiber channel, NFS, SMBM. And based on user's request, and the system in need to run a sequence of commands, right, to carve the storage, partition, or format, and then make it available. And in Kubernetes, so we are trying to use object to represent, right? Again, to mimic the relationship between the user and system in. So from user side, basically it needs some request. So we use so-called persistent volume claim to represent a request for storage. So here we have an example that in the persistent volume claim spec, you can define what's the size of your storage and what is the access mode for your storage. And also you can define what's the file system you want to put for your storage. And you may notice there's no detailed information about the actual storage at all. You don't know what is the actually underlying storage type, whether it is NFS or it is SCSI, and there's no like a disk ID there. So the benefit of this way is it makes your workload very portable, right? So if you need to migrate your workload from one class to another, right, you can just use exactly the same PVC, right? There's nothing you need to change. And also with PVC, the Kubernetes can manage the volume lifecycle independently from their workload. And then, but down to the end, right, the controller still needs to access, be able to manage the storage. So where those detailed storage information stored. So we have another object to store those information we called persistent volume. So this is an example of such spec. So in this example, it specifies what's the size of, what's the capacity of this storage, and what's the available volume access mode, and what is the file system, and also what is the driver for this storage. And the detailed volume ID basically is a handler so that you can access the volume. And for user side, right, it creates a PVC, so just a claim. And system inside, right, it need to create those PV objects to represent those volumes. And the system will binding these two objects. Binding here means you will have pointers to point to each other. And now the controller can use that pointer to find out from this claim, right, to the actual volume information. And next, Manu will talk about different ways of binding or mapping between PV and PVC.
Okay. I'm covered. Thank you, Jing. So moving on, I mean, we covered a couple of things. We covered like what are the differences between imperative approach and the declarative approach that containers have. And I think that's something to consider as you're designing the architecture about completing a task. We also covered like how does Kubernetes abstract storage by storage classes or PVC mapping, so that way your application is portable, independent of the underlying architecture. Now let's look at when you're designing your architecture. If you, coming from a VM world, one of the things I've seen a lot of folks do is around, depending on the level of control you want around allocations. Like if you're using an external storage, a lot of folks will just create, let's say, 10, 100 gig volumes and say, this is my standard size, these are the volumes, these 50 are to be assigned to this application, these 50 are for this other applications, and the two shall never converge because you're worried about workload incompatibilities or because processors may be shared on an external system. So mapping the same parallels to the container world. In containers, you actually can do a very similar thing. You can actually have pre-provisioned volumes where you actually can dictate that these are the set of volumes that can be mapped, and the system cannot dynamically create. Or you can create more flexibility to the application and say, well, let's talk about dynamic volumes. So getting into it, so pre-provision, and sometimes also called static provisioning, is where a storage admin can pre-create a set of volumes. And whenever a container gets deployed and asks for a volume through a storage class and a PVC mapping, the only option is one of the pre-created volumes. If the volume doesn't exist, the request fails. If the volume exists, the request goes through. But you cannot create more than what you are allocated. So it's an interesting way of creating that paradigm where you can control how different things are mapped. Other piece I also want to mention over here is, if there is a scenario, especially with stateful applications, where you have a backup, you restore the backup into a particular volume, and when your workload comes up, you really don't want any volume but that particular volume itself to be mounted. There is a way around PVC mapping where you can force a container to be mapped to a certain specific volume. This case comes in when you have like restores or backups, and then you have a very specific value to be mapped up. So that is also part of pre-provisioned or static provisioning. In the dynamic provisioning, the biggest difference is that depending on the storage policies across the environment, you may allocate a set of storage pool and say, as long as this like a 1 terabyte pool, dear application admin, have at it. Create as many volumes, create whatever size, but this is the area and you can just use 1 terabyte of pool. Or you can allocate multiple sets of pools to say, one is my SSD, one is my spinning drive, 7.5, 15K drives, whatever the pool configuration is. But the actual volumes are not pre-created. They are created on demand when a container spins up or a workload is deployed. So again, it depends on what are the policies across your environment for managing VMs. And if you want to translate the same policies, the same level of controls, they can be mapped to the container side, and container supports both of those policies itself. We've seen both models being viable, but the biggest difference comes in like if you are running workloads on-prem or you're running workloads in the cloud, there is a difference. If you're in the cloud, you actually end up more on the dynamic provisioning side. And if you're running on-prem and you're concerned about that, you actually do you can do static provisioning too. Is it a noise? Sorry. So we talk about storage classes. Storage classes, can you guys hear me okay? Okay. So storage class is a way which basically allows storage or infrastructure admins to provide controls. You can actually you can create classes and give them names like this is my fast class, slow class, or slower class. And within that parameter, you can define what is the provisioner. Provisioner is usually like a CSI driver to say, depending on what storage vendors you're using on-prem or what type of storage you're using in the cloud, each of them will have their own storage providers or storage provisioners. And then you can define what type of interface and the disk it is inside. So it gives you those controls within that. Within storage class, depending on the type of storage provider you're working, there could be custom parameters also passed to expose certain vendor-specific information also. But at a base level, there is a general set of parameters that can define what kind of service the application needs. Now, before we get into this, so we've thought about the architecture, we're starting to deploy applications, we have figured out whether we wanted to use dynamic provisioning or static provisioning. Now we start deploying applications, and applications start consuming storage. Then the question becomes, how do you maintain state where, because of the dynamicity of the environment, when you scale, you really don't scale beyond the certain level of controls that you have. So on day 3, I want to talk more about how do you set boundaries and controls in that environment. So one of the things we can do is set quotas. When you can set quotas on how many PVCs an individual namespace can allocate when it's growing or scaling up and scaling down. And in that case, you can, like in this example, you can say there are 5 PVCs and the total capacity cannot be more than 50 gigs. Now, the application has flexibility to define how many of those, but the total is capped at 50. So it gives admins a way to control the scale and the dynamicity, but still give flexibility to the application admin to say, you can still do what you want, but these are the limits that are defined in that space. The next level of control we can look at is limit range. So depending on what type of box you want to give for the application admins, another way to do it is that, like especially coming from a VM world, particularly storage admins, there was a general rule depending on the scale to say any volume less than 100 gigs, go ahead and it's automated, you can create it by yourself. Anything over 100 gigs, well, let's talk about it because I may need to do some capacity planning or things around it. If I translate the same concept over to containers, within this, you can define limit ranges to say any volume between, let's say, 1 or 2 gigs, we'll just take an example, can be done automatically. But anything beyond that, it needs to be a special request. So if you're a storage admin, you're controlling what your scale is going to be. This is another way where you can define certain limits depending on what your corporate policies are, how you want to manage growth, how you want to manage scale, and how you make sure the applications don't step on each other, given a lot of the environment is going to be shared, at least on the back end. So here's the cheat sheet. So we talked about PVPVCs. We talked about static provisioning, dynamic provisioning. We talked about CSI drivers. Essentially, a lot of these concepts are very similar. They have different names, they have different titles, but at the end of the day, the level of controls are more dynamic, but they can be translated to something that you're already aware of. So we start with a storage class. A storage class is a storage profile. In containers, the main goal is to abstract application from any physical characteristics of a storage. You don't care whether it's FC, iSCSI, all you care is, I am writing to this storage class, and when my application moves from environment A to environment B, as long as that storage class is available, I am fine. I'm not worried about what's serving that storage class. Next thing is, PV is more about kind of going back to the imperative way of modeling of request. PV is an actual storage object. Say, here's my volume, this is how you map it. So it's almost like a volume, it's an object that is representing volume in containers. PVC is a request for a volume. Again, going back to the data models, this is you request and then you get it, and Kubernetes works on achieving that state. Controller is that manages the whole thing on how to get to a state that was requested. If the resources are not there, it will keep trying versus I failed. There will be timeouts, but that it works on it. Static provisioning and dynamic provisioning, depending on, again, your policies for the environment that you're using for VM and containers, you can leverage that. Static provisioning allows you to limit provisioning to pre-carved out volumes. Dynamic provisioning allows you to create dynamic volumes on demand given a storage pool or a pool of storage. And you'll hear multiple terms around CSI drivers, in-tree drivers. The biggest difference is in-tree drivers was previously the way storage partners integrated into containers. CSI is the new way, and a lot of drivers are moving. The biggest difference being in-tree drivers were part of the Kubernetes stack. CSI drivers are external interfaces which storage partners write to it. But if that term comes up, it essentially is a storage interface that storage partners and vendors use to integrate into the container stack itself. So hopefully this helps you move and translate terminology from A to B, basic concepts around how you can look at containers, how you look at storage. And if you're used to certain practices and at operational level or on architecture level on a VM world, this will help you kind of map those to if you're moving on to the container side. Thank you so much for taking time this afternoon. And if there are any questions, we can definitely help answer them.